Welcome to Algo Guru. On this video, we are going to look at bit manipulation. In problem solving, we can use bitwise operators to do multiple problems. We can come up with solutions in certain cases pretty fast. But one thing to know is that these questions are not like that common in a lot of coding interviews unless you're interviewing for a position like system level programming or kernel level programming. But still, bit manipulation is something which is very good to know because these are very fundamental stuff. This is working on primitive data types. If you look at how the computer works when it comes to dealing with integers and characters, this is something very important to know. So let's jump in and look at a few problems. All right, so I got like a dummy class called bits, and then I have a test function which will be like testing some of the test cases that we are going to come up with. And let's start with the first problem. The first problem is creating power sets. You might be already familiar with creating power sets, and there are so many different ways of doing it. And it'll be very interesting to know that it can be done using bitwise operators. So in this particular example, the string is ABC, and the power sets, there are possibly 8 different power sets. The first one is an empty string, and then A, B, C, AB, AZ, and ABC. So these are the power sets. So how can we get all the power sets of a given string, which is S? Not a real difficult thing to do. The first thing to do is get the value. Uh, Basically, like getting the value of uh, the length of the string. And the second thing to do is to get the total number of power sets. So that is calculated using the POW, which is a standard library function to get the power. So get the 2 to the power n. So in this example, n is 3 because the string is ABC. So 2 to the power n, which is 2 to the power 3, is 8. And as we have seen in the example, there are 8 possible power sets. So once we have these two values, it's pretty straightforward. Like int I is equal to 0, I less than power, and plus plus I. And then there will be an inner loop. So that is starting from j is equal to 0, j less than, and that's pretty much it. And now what will we check? So we will check something like this. So in that particular if condition, what I'm doing is I will take I and I will AND that with 1 left shift by j, number of times j. So the first time it will be 0, next time it will be 1, the next time it will be 2, and it will go up until like less than the length of the string. And if that is the case, then what it is going to do, it is going to print that particular character at that particular index. I think that's pretty much it. I cannot think of anything beyond that. So let's see how this is going to come up with. This should be like something which is pretty straightforward. But let me see. I got there is a small. All right, so I just had to change like this C out, move it outside the for loop. Otherwise, it was like totally messing up things. So let me run the test case, and this is what I got. The first one is an empty string, and then it is A, B, A, B, Z, A, Z, B, Z, A, B, C. The only problem with this is that it's not going to print everything in order. Like you see, after A and B, C comes after A, B. So it is not guaranteed that it will print all the power sets in order. So if you don't need to have that in order, then this is a perfect thing using like just bitwise operators, and you can do it. And the next problem that we are going to look is count set bits. It's another very interesting problem. So what does this mean? Like I have two examples here. Like for integer 3, the total number of set bits are 2. So integer 3 in binary is 1 1. So that's the reason. So this is counting like the number of ones. So the number of ones is 2 for integer 3, and for integer 25 it is going to be 3. So let's see how we can do this. So first I will declare a count, which is equal to be count is equal to 0, and then a while loop where as long as like x greater than 0. So count, what I can do is like I will increment the count when x and 1 is equal to 1, and then I'm going to return the count. So pretty straightforward, as you can see, like while x is equal greater than c, increment the count, and then right shift x by 1 every time within the loop, and as soon as like x becomes 0, it's going to come out of that loop, and then it will return the count. So let's come here, and this is what it is, 3. I'm going to make it a little bit more something more cleaner way of doing things. See out, and the second one is 25, and it's going to return count bits in 3 is 2 and count bits in 25 is 3. Make sure to do this problem by yourself and see like how it is working for. All right, next is multiplication. You can multiply two numbers without using the asterisk or the star symbol, and again you can do that just using like bitwise operators. Let's see how we can do that using bitwise operators. So I'm going to pass two arguments which are long, and then I will also need a result which is going to be 0, and then I will also have an index 0. So again, like we have seen last time, we will have a condition like x greater than 0, and the first thing to check is we are going to take a look at each bit of x and see whether it is a set bit. So in this case, x and 1 is equal to 1. So we will need like something like this, and then after that all we got to do is y left shift by index, and the first time this is going to be 0, remember that, and then yes, we are going to right shift. We are going to right shift x. So let's take a look at this problem. It's pretty easy. First x is going to be greater than 0, and at every bit the least significant bit, we are going to check whether it is set. If it is set, then what we are going to do is that we will come inside this if condition, and then we are going to append the result by left shifting the index. And how the left shift is calculated is based upon this one. How many times this while loop gets run, that's how many times this index will get incremented. And after that, in every while loop, we are going to do a right shift of x to one position, so that at one point it will become 0 and it will exit. So here we have two examples like 5, 11 and 9 and 3. So let's go there to the test case and let's do that. We had like 5, 11 and 9, 3. 5, 11 and 9, 3. Multiply 5 and 11 and multiply 9 and 3. Let's see what this is going to bring up. 5 and 11, multiplying 5 and 11 is 55, and multiplying 9 and 3 is 27. That's pretty much it. All right. So let's now go to the, like with division, we can also, like with multiplication, we can also do division using the bitwise operators. So in this example, I have 25 and 5, and the quotient is 5, and 76 and 7, and the quotient is 7, which we will see. We will see whether this is correct. I think this has to be like 10. That's what I would expect. All right. So I'm going to have a function long x, and then I'm going to have the result is equal to 0, and then I'm going to declare an int power, which is going to 32, and then I'm going to have a p underscore y, which is a static cast unsigned long y left shift by power, and all right. After this is again going to be like a while loop. So there is a trick here. You cannot do like x greater than 0 because you are now up against y. So when you start, like for example, like 25 divided by 5, you will come down, and then even when 5 divided by 5, it still should work. That's the reason y is greater than or equal to y. And inside this, there will be another while loop, which will be like greater than x. And that while loop is going to be this. And then result is equal to 1u power. So that's pretty much it for this one. So There are two while loops, as you can see, and then basically what it is going to do is that it keeps incrementing the p underscore y, which is a power value of y, by left shifting y by number of times, like 32 times, and then keep decrementing that and keep decrementing the power value, and then keep adding like result over here by left shifting 1 by number of times power it is, and then again decrementing x by this value, and then just divide, returning the result. So let's try divide, 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 divide. 25 divided by 5, and 76 divided by 7, 25, 5, 76, 7. That's it. 25 divided by 5 is 5, and 76 divided by 7 is 10. That's pretty much it for division. It's pretty straightforward. Just try to go through this video multiple times if you need, just to understand like how this works. So the next problem is like swapping bits. So I have an example test case here, like 69, and I give like two indexes, I is equal to 1 and j is equal to 6. So I have to swap the bits at index 1 and index j. The result is 7. So why is it 7? So 69 in binary format is 10000101. And then while swapping bits, so this is 1 and this is 6. Okay? So when you swap those, it becomes something like this, which is 7. And the trick over here is that in this case I'm swapping bits 1 and 6. What if both 1 and 6 are the same, whether they are ones or zeros? There's no point in swapping, right? So the first thing that we need to check is that the bits over there are different. Only if it is different, we are going to swap them. So let's do something like this, and int I comma int j. All right. So the first thing that we need to make sure is that x right shift I and 1 not equal to j. That's what we are going to do. So right shift x I times and add it by 1, and right shift x by j times and add it by 1, and this should be different. That is where like we make sure that the bits are different. It's not 1 and 1, and it's not 0 and 0. It is 1 and 0. It has to be different. If it is different, then come over here, and I'm going to create like an unsigned int mask. So what will be that? I'm going to ref shift by I, and then I'm going to OR it by j. And then all I'm going to do is that I'm going to mask and then return x. That's pretty much it. Very simple stuff. Let's see how 69 is going to work on this one. Okay, swap bit 69 9 at 1 and 6. 69 at 1 and 6. And there you go. Swap bit 69 at 1 and 6 is 7. It just did what we really wanted it to do. It's pretty straightforward stuff again. And the next one that we are going to look today in this video is the closest weight. It's also pretty much something very interesting. I have two test cases. So the input is 6. And what is weight? Weight means the number of set bits. So X has 2 set bits. That is 6. 6 has 2 set bits. So find a value which is very close to 6 means that number should also have 2 set bits, and then the difference between that number and X should be the minimum. So in this case, the closest weight is 5. So X is 110 and 5 is 101. Both has 2 set bits and difference is just 1. Take a look at 8. 8 has just 1 set bit and the closest weight is 4. 8 minus 4 is 4. So with just 1 set bit, the closest that you can get is 4. So let's take a jump into this one and see what we can do. So here it's a little bit tricky actually, because you have to actually go through a loop, going through like all the 64 bits kind of thing. But again, there is a trick, like something very similar to what we did over there. I and 1. Okay, so we have to make sure, again, something like this, like we will make sure that these are different. This is very similar to what we have seen in the last one. We are just making sure that the bits are different at that point, and then we are going to create a mask. Again, 1L left I, 1L left I plus 1. And then XOR with the mask and return mask. This is just a safe condition over here, because sometimes the compiler will complain that, okay, you don't have a return at every line, something like that. So again, come here, swap bits closest, like 6, closest to 6, and then closest to 8, closest to 8. Well, I have a small mistake over here. Instead of mask, I have to return X. So I'm going to return X, and here it is. Closest weight 6 is 5 and closest weight 8 is 4. That's pretty much it for this video. We covered some of bitwise operator problems, and I know that I've been going pretty fast. The reason is that I don't want to like spend a lot of time and come up with an hour-long video for like 5 problems, because the video is out there. You guys can always go back in, watch it again and again, and try to reproduce it. That's going to be the key. Try to reproduce these as many times as possible so that you can just do it any time of the day or night. So do it, come back, and we will go through some more of bitwise operator problems in the next video. Thank you.